Hello, students. We are now to the lesson for, as you can see on the board, Monday the 30th, which would be our first day back from our regularly scheduled spring break. And so as we look at what was on the agenda that day, um, you were assigned the conjugate acid base pair assignment on the Friday before spring break was to begin. And so I ended up not collecting that assignment, but please make sure that you check the answer key so that you know that you make sure that you're aware of how to do all of those things. And if not, please let me know and email me. So today we're going to continue the acid and base notes. Today we're going to look at pH and pOH calculations and their relationship to hydrogen ion concentration and hydroxide ion concentration, and also to how acidic or basic a solution is. The homework assignment today, which is entitled pH and pOH, as you can see here, page 172, would be due tomorrow, the 31st. Okay. All right, so now we're going to look at, we're going to start with water, the importance of water in acidic and basic solutions. So remember, water molecules are very polar, all right? There's a separation of positive and negative charge in its structure due to the electronegativity difference between oxygen and hydrogen. Remember, oxygen, since it has a higher electronegativity, is going to be have the slightly negative charge. The hydrogens going to be slightly positive charge. Because of that polarity, a hydrogen atom from one molecule can be attracted to the oxygen atom from another water molecule. And what ends up happening is water molecules react with one another. This reaction is called the self-ionization of water or auto-ionization of water. So here's what happens. So we have two water molecules here that react together. And again, the negative charge associated with that extra pair of electrons and a coordinate covalent bond then happens between that pair of electrons and a hydrogen atom from another water molecule, coordinate, a covalent bond, right there. And what you end up getting then is, right here is that coordinate covalent bond here, which is how the hydronium ion is formed. We talked about the hydronium ion in regards to Bronsted-Lewis acids and bases. And then what's left behind then from the formation of the hydronium ion from that second water molecule is a hydroxide ion. Here again, this reaction is reversible. It goes in both directions simultaneously. As two water molecules react to form a hydronium and hydroxide ion, those two ions attract one another and again form two water molecules. So without the bonding that we show here, down here then is the reaction written in its normal way. And again, this is called the self-ionization of water or the auto-ionization of water. Now, before I go too awfully far here, I want to say that this reaction that we just talked about right here, this is the real version of the auto-ionization of water. This is what really happens. However, there is also a shortcut reaction. So I'll call this the shortcut version. Whereby rather than having two water molecules react with one another, which is what really happens, we just show it as one water molecule breaking down into a hydrogen ion now and a hydroxide ion. So as you compare those two reactions, the real one versus the shortcut, you can see that these two products are the same. And we are substituting a hydrogen ion here for a hydronium ion. Keep in mind that a hydronium ion is a water molecule that has a hydrogen ion attached to it. So basically, it's a hydronium ion could be called a hydrated hydrogen ion. So I don't want that to confuse you. Like I said, this is what really happens. But in many texts and in a lot of your readings and in your future studies, you're going to see it written this way more often than not, if for no other reason than just to save time. So in pure water, the forward reaction, remember this is a reversible reaction, the forward reaction occurs only to a very small extent. The hydrogen ion concentration is 1.0 times 10 to the minus 7th molar. In the real version, that hydrogen ion concentration, of course, would be the hydronium ion concentration. Again, keep in mind that these two are interchangeable. All right, they're interchangeable. When we talk about one, we mean the other. So, as you can also see then on the next page, the hydroxide ion concentration in pure water is the same, 1.0 times 10 to the minus 7th molar. These brackets, by the way, as we say here, refers to the concentration of in molarity. This is the concentration unit that we use in acid-base chemistry, and that is molarity. So as you can see, the hydrogen ion concentration and the hydroxide ion concentration are equal. When that is what makes what we call water a neutral liquid. All right. Look at the concentration of water molecules in pure water, 55.6 molar. Hydrogen ion concentration, 1.0 times 10 to the minus 7th molar. Hydroxide the same, and yet water 55.6 molar. That is a big difference, all right? 8 decimal places different if you want to get right down to it. So actually closer to 9. So what that says is this. In a given sample of water, it is nearly all composed of water molecules and very, very few hydrogen ions, hydronium ions, and hydroxide ions. All right. So the auto-ionization of water occurs only to a very small extent. As quickly as these ions are formed, they react with one another and rejoin and form water molecules. So even though this reaction is reversible, if I was being more accurate in depicting it, I would draw my arrows like this, rather than like that. This kind of makes it look like that the forward reaction and the reverse reaction occurs to the same extent, and that is not true at all. Not in this case, anyway. So again, since both the hydrogen and hydroxide ions concentrations are equal, pure water is then termed a neutral liquid. And for any aqueous solution, the product of the hydrogen ion concentration and the hydroxide ion concentration is equal to a constant, 1.0 times 10 to the minus 14th. If you multiply those two together, that's exactly what you get. And that is also true for any other aqueous solution. And this is known as Kw, or the ion product constant for water. All right. All right. So let me advance this. So in a neutral liquid or a neutral solution, the hydrogen ion and hydroxide ion concentrations are equal. All right, they are equal. In an acidic solution, that is not the case. In an acidic solution, the hydrogen ion concentration is greater than the hydroxide ion concentration, meaning the hydrogen ion concentration is greater than 1.0 times 10 to the minus 7 molar, and the hydroxide is less than that. In a basic solution, it's just the opposite. In a basic solution, the hydroxide ion concentration is greater than the hydrogen ion concentration, And so the hydroxide ion concentration is greater than 1.0 times 10 to the minus 7th, and the hydrogen ion concentration is less than 1.0 times 10 to the minus 7th. Now, rather than using hydrogen and hydroxide concentrations as the only means of determining acidity or basicity, there has been devised a scale that uses small whole numbers rather than the actual concentrations to do that. And that is the pH and the pOH scales. So in addition to using actual concentrations to measure the strength of acids and bases, the pH and pOH scales are also used. pH, which stands for power of hydrogen, of a solution is equal to the negative logarithm of the hydrogen ion concentration. That's log base 10. All right, so on your calculator, you should have two log keys. One is log. We've used that before when we used it for nuclear decay, radioactive decay. The other key is natural log ln. We are using log base 10. Okay, so the pH of a solution is equal to the negative log base 10 of the hydrogen ion concentration. The greater the hydrogen ion concentration, and thus the stronger the acid, the lower the pH. So think about that. So if we have a hydrogen ion concentration, for example, of 1.0 times 10 to the minus third, all right, molar. And we'll do the calculation here in a second, but the pH of that would be equal to 3, all right? If the hydrogen ion concentration was equal to 1.0 times 10 to the minus 1 molar, then the negative log of that, the pH would be equal to 1, all right? So think about that. Which of these two concentrations is greater? Well, 1.0 times 10 to the minus third is 0.001 molar, while 1.0 times 10 to the minus 1 is 0.01 molar. 0.01 molar is 100 times more concentrated than 0.001 molar, and yet the pH is lower. That's what we're talking about here. Since it's a logarithmic scale and it's the negative log, as the concentration here gets stronger, the pH gets lower. All right, so here I had us just doing a little quick calculator check to make sure you remember how to use the log key on your calculator. All right, and again, before I go too far here, and remember that in reality, that the pH is the negative log of the hydronium ion concentration. If you ever see that, don't let that confuse you. Because remember, we use hydronium ion and hydrogen ion interchangeably. Okay, so don't let that confuse you. All right, so here we have the hydrogen ion concentration of an acid is equal to 4.52 times 10 to the minus third molar. What is its pH? All right, so pH is equal to the negative log of the hydrogen ion concentration, so it would be the negative log of 4.52 times 10 to the minus 3. So depending on what type of calculator you have, some of them you would do this in the exact order. Hit your plus or minus sign, then the log base 10 key, plug in your number here, close the parentheses and hit equals, and you should get the answer. Other calculators, you put this number in first, and then hit the log key, and then hit the plus or minus key last. So it'd be the exact order you do this. Depending on the model you have, I can show you real quick. If you have a model such as this, you're going to do this in the exact order it's written, which is a TI. If you have a Casio of some kind, in all likelihood, you're going to do it in the exact opposite order. Put the number in first, then the log key, then the plus or minus sign. Either way, check that on your own. Make sure you get the right answer. And the 3 sig figs, that pH comes out to 2.34. So go ahead and do that on your calculator, do a quick check, and make sure that you get that answer. Notice here that the pH has no unit, all right? It is a dimensionless number. Just the number itself, no unit. So the pH scale runs from 0 to 14. Remember we said the lower the pH, the stronger the acid. So pH 0 is the strongest type of acid. When you get to 6.99, that is the weakest acid. So basically anything under 7 is acidic, but the lower the pH goes, the more acidic it gets. pH of 7, of course, is neutral. And once you get above 7, up to a maximum of 14, that would be a basic solution, all right, a base. So this would be a strong acid. This would be a weak acid. This is neutral. This would be a weak base. And this would be a very strong base. Okay? pOH. It's just an analogous scale for bases, set up the exact same way that the pH scale is set up for acids. So pOH stands for power of hydroxide, and it's equal to the negative log base 10 of the hydroxide ion concentration. And once again, the greater the hydroxide ion concentration, the stronger the base, the lower the pH, and thus the higher the pH. We just said pHs that are large, greater than 7, are basic. pOHs, on the other hand, are small. So it's just like the inverse, or the reverse, I should say, of acids. So the pOH scale runs the same range, 0 to 14. pOH 0 would be a very strong base. 699, a weak base. pOH 7, of course, is still neutral. And then once you get above 7 for a pOH, the solution becomes acidic. So this would be a weak acid. And then up to 14 would be a very strong acid. For a particular solution, a little star here, the relationship between pOH and pH is that they always add up to 14. So if you have a solution with a pH 5, then its pOH would be 14 minus 5, or 9. And based on that, either one, pH or pOH, that would be a fairly weak acid. If the pH is 13, then the pOH would be 14 minus that, or 1. That would be a very strong base. pH 7 and a pOH of 7, of course, that would be a neutral solution. One thing I want you to understand or reiterate from what I said just a little bit ago is that the pOH scale is logarithmic, log base 10. What that means is every time you change a pH unit, you are changing the actual concentration of the solution by a factor of 10, not 1. So, if somebody says, well, pH of this solution is 3 and the pH of this solution is 6. You say, okay, well, this solution is obviously more acidic than this one, but how much more? Well, this one has a concentration of 0.001 molar. This one is 0.00001 molar. All right. You say, well, they're different by 3 pH units. Well, yeah, they are, but 3 pH units, you got 3 to 4, 4 to 5, and 5 to 6. That's 3 powers of 10, which is 10 times 10 times 10, which is 1,000. So 3 pH units, even though they're both acidic, this solution is 1,000 times more acidic than this one. You don't really get that effect with the pH scale until you look at it in terms of its actual concentration. That's something I wanted to make sure you understood. Okay. All right. So to summarize, I keep walking over there because my computer is normally over there to move the scroll it up, but maybe I'll figure old habits are really hard to break. Okay, so here's a summary of the acid-base solution relationships we've been talking about today. So for any aqueous solution, the product of the hydrogen ion concentration and the hydroxide ion concentration for that solution is equal to a constant. That constant is equal to 1.0 times 10 to the minus 14th, and that is called Kw. The pH of a solution is equal to the negative logarithm, log base 10, of the hydrogen ion concentration. pOH is equal to the negative log of the hydroxide ion concentration. For any particular solution, the pH and the pOH of that solution add up to 14. So if you know one of them, you can get the other one by simply subtracting it from 14. And then if you want to go the opposite way, right, if you want to find the hydrogen ion concentration from a pH, then rather than using log, we will use inverse log, for which on most of your calculators the button is labeled 10 to the x, all right? So the hydrogen ion concentration would be the inverse log of the negative pH, again, don't forget that negative sign, or 10 to the negative pH, and then analogous equation for hydroxide concentration. Inverse log of the negative pOH, or 10 to the minus pOH. All right, so we got a example, a couple of them here, I think. Oh, maybe just one. All right, so let's do this one. So the hydrogen ion concentration of a solution is 2.50 times 10 to the minus 10th molar. That's a pretty small number, all right? Remember, 10 to the minus 7th molar is neutral. So if you're getting, if the pH is, or if the concentration of hydrogen ions is greater than that, or smaller than that, I should say, then we're looking at something that's probably pretty basic. We'll find out here in a second. So first it wants us to find the pH, all right? So we have a direct link between pH and hydrogen ion concentration. pH is equal to the negative log of the hydrogen ion concentration, so the negative log of 2.50 times 10 to the minus 10. And again, to 3 sig figs, that would be 9.60. pOH. Well, if we know the pH of a solution, we can always get its pOH very easily because the two together add up to 14. So the pOH then would be equal to 14 minus the pH, or 14 minus 9.60, which would give us 4.40. Now, normally, I realize that in subtracting, we would leave, since this is a whole number and this is 2 decimals, that we would round to the whole number. But in this case, I would want to tell you that pH plus pOH equals 14. That 14 is a constant, and so the constant doesn't come into play here. So if this is 2 decimals, that's what we leave our pOH at, is 2 decimals. C, the hydroxide concentration. Well, we have a link between hydroxide concentration and pOH, so we'll use that. So the hydroxide concentration is equal to the inverse log, right? The inverse log of the negative pOH, or like I said, on most of your calculators, that button is labeled as 10 to the x. So that would be 10 to the negative pOH, which would be 10 to the negative 4.40. And again, to 3 sig figs, that would be 3.98 times 10 to the minus 5th molar. Don't forget the unit on this one. Remember, hydrogen concentration and hydroxide concentration are labeled with molarity. All right. And again, 3 sig figs there. There is another way that you could have done this, calculated this. Put a little star there. Probably takes the punching a few more buttons, but it will show it to you. Remember that Kw for any aqueous solution is equal to the hydrogen ion concentration times the hydroxide ion concentration. So that would mean then that the hydroxide ion concentration would be equal, if we divide this out, to Kw over the hydrogen concentration, which would be 1.0 times 10 to the negative 14 over, here's our hydrogen ion concentration, 2.50 times 10 to the minus 10. And if you do it that way, you get 4.0 times 10 to the minus 5th molar. And if you look at those two, they're essentially the same. They're rounded a bit differently, of course. You know what? This should actually have 2 sig figs, just like this one, because here again, this is a constant. So my bad on that. But as you can see, these two are essentially the same answer. This one is a little bit more precise doing it this way. I don't care which way you do it. Like I said, you'll be pushing less buttons if you do it this way, but I'll leave that up to you, however you want to do it. So in the end, is this solution acidic or basic? Well, you could look at several things here to answer that. I guess the easiest way for me would say, well, just look at the pH. And it would be basic because the pH is greater than 7. You could have just as easily said that the pOH was less than 7. You could have said that the hydrogen ion concentration is less than 1.0 times 10 to the minus 7th molar. You could have said that the hydroxide ion concentration is greater than 1.0 times 10 to the minus 7 molar. So there's 4 different ways, basically, that you could have explained that. Again, the pH scale is used so much more commonly, I would say, than the others, that that's just the one I naturally turn to. But again, I would accept any of those answers. Okay? All right, the last thing with today's lesson involves the strength of an acid or base, comparatively speaking. How do we determine that? So an acid or base is referred to as either strong or weak, depending on the degree to which it dissociates or ionizes when it's dissolved in water and forms an aqueous solution. A strong base ionizes, completely, 100% in aqueous solution, meaning when you dissolve it in water, every last molecule, every one, 100% of them, split apart and ionize into ions, all right? Strong bases include the soluble metal hydroxide compounds of group 1A and 2A. So if a metal hydroxide is in group 1A or 2A and it is soluble based on the solubility rules, then it will form a strong base. Likewise, a strong acid ionizes completely, 100% in aqueous solution. And there are only a limited number of acids in which that's the case. Again, strong acid means that 100% of the molecules split apart into ions. And they are hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric acids. There are 7 of them, all right? And those you will need to commit to memory, all right? As well as which bases are strong. So here's an example of a strong acid, hydrochloric acid. Notice now that this arrow is only pointing in the forward direction, like a normal equation. That is because none of these ions combine then to reform hydrochloric acid molecules. 100%, once the reaction is, once this HCl is dissolved in water, there are no HCl molecules remaining. Every single one of them has split apart into hydrogen and chloride ions. Okay? Just as it says right here. Now, a weak acid or a weak base, so here's an example of a weak acid, acetic acid, only slightly ionizes in an aqueous solution. Normally, that weak acids are less than 10% ionized, which means then when you dissolve that molecule in water, as it splits apart into ions, many of them join back together and form the original acid molecules. So now again, we have the reversible reaction sign there. So a weak acid only slightly ionizes, all right? Only slightly ionizes. In this example, once the acetic acid is dissolved in water and forms a solution, once it's all said and done, only about 5% of the molecules remain split apart as ions. The other 95% of them have rejoined and formed acid molecules. So again, the double arrow there refers, it's on the next page, the double arrow refers to the equilibrium established between ion formation and then the molecules reforming. And as you can see, the reaction is tilted heavily to the left. At the end, we have almost all of this. So again, if I was drawing an arrow that was more depictive of this actual situation, I'd have probably drawn it like that. But we don't do it that way. But this, again, is kind of misleading. I think it kind of leads you to believe that, oh, well, these are the same on both sides, when in reality they're not. Sometimes they can be, but not in this case. Okay, so, excuse me. So to calculate the concentration of hydrogen ions in a weak acid, we take the concentration of the acid and multiply it by the percent ionization, expressed as a decimal. All right? So if it's a strong acid, remember, the percent ionization, so if it's a strong acid, the percent ionization is 100%. And 100% expressed as a decimal is 1. All right? So for instance, if this was a strong acid and it was 0.5 molar and its percent ionization is 100% or 1, then the concentration of hydrogen ions would also be 0.5 molar. It would be equal to the acid because, again, in a strong acid, all of the acid molecules ionize. In a weak acid, that is not true. So we could use this to describe the hydrogen ion concentration of any acid, but again, if it's a strong acid, that's 100% or 1, and so it's the same value. So let's do an example like this one. So for a 0.0300 molar acetic acid solution that is 9.50% ionized, so that means 9.5% of the molecule is ionized, and the rest of them remain as acid molecules. Calculate the hydrogen ion concentration and all these things again. Okay, so first, hydrogen ion concentration. So the hydrogen ion concentration now is going to be equal to the acid concentration, which is acetic acid. Oops, if I could write it correctly. There we go. I'll blame Mr. Shaw for that. He insisted that I go to lunch before I do this lecture, so I now have a belly full of food and I'm somewhat sleepy and my mind is wandering. So thanks, Mr. Shaw. Yep. Actually, I am thanking him because, one, for him, I wouldn't be able to do this. So anyway, so this would be the acetic acid concentration. times the percent ionization, all right, times the percent ionization. Again, expressed as a decimal, we can do that right now, so we move that 2 to the left, so we can 0.0950. So that would be 0.0300 times 0.0950. And so our hydrogen ion concentration, let's see, looks like three decimal places. That first zero isn't, first is zero after the decimal place, not significant, would be 2.85 times 10 to the minus third molar, or 0.00285. Okay? All right, pH. Okay, so the pH is equal to the negative log of the hydrogen ion concentration, which we now have. So it'd be the negative log of 2.85 times 10 to the minus third. And again, the 3 sig figs, that would be 2.55. Now that's a pretty low pH. Keep in mind, this is a weak acid, all right? Strong acids have pHs down in the range around 0, okay? pOH. Remember, pOH and pH add up to 14. So the pOH would be 14 minus the pH, be 14 minus 2.55, which would be 11.45. Again, we keep our 2 decimal places because this 14 is a constant. Okay. And then lastly, the hydroxide ion concentration. So the hydroxide ion concentration is equal to the inverse log of the negative pOH, which again on most of your calculators is depicted as 10 to the x. So that would be 10 to the negative pOH, which would be 10 to the negative 11.45 power. And again, to 3 sig figs then, based on our original data, 3.55 times 10 to the minus 12 molar. All right. Again, there's another, we could have done this the other way, like I showed you a few minutes ago, and I'll leave that up to you as to how you want to do it. Before I end today's lesson, there's one thing I want to bring up. So this is acetic acid is obviously an acid, all right? And obviously it has hydrogen ions in it. It obviously has acetate ions in it. But as you can see from our calculations, all right, it also has hydroxide ions in it, all right? 3.55 times 10 to the minus 12 molar of hydroxide. So the question is, this is an important one. Where do the hydroxide ions come from in an acidic solution? Where do they come from? Because they sure as heck don't come from the acid, all right? But think about solution. What is the acid dissolved in? All right? The acid is dissolved in water. It's dissolved in water. Remember, when you dissolve this acid in water to form a solution, not only do you have acetic acid molecules and hydrogen ions and acetate ions, but remember, you've got water molecules in there that are self-ionizing. Remember the self-ionization or auto-ionization of water? Even though that occurs to an extremely small degree, there are going to be hydroxide ions in this solution. Not very many of them. I mean, look at the difference. Hydrogen ion 10 to the minus third, hydroxide ion 10 to the minus 12. That's 9 decimal places different, 1 billion times less hydroxide ions than hydrogen ions. So the solution is still extremely acidic, all right? but there are hydroxide ions in there. It's not just made up from the calculation. It comes from this fact right here, that there are water molecules in there that are self-ionizing. And even though they self-ionize to a very small degree, there are still some in there. All right? And the same thing applies to bases. There are hydrogen ions in basic solutions. Not very many, but they're there. The answer to both of those is right there. Right there. Okay? That ends our lesson for today. As stated on the do nows, you have an assignment, pH and pOH, that would be due tomorrow as far as our regular schedule goes. Again, the video for this lecture as well as the answer key to the assignment are all found on as links on my homepage on Canvas. And so once you have your homework completed, please check it there. And if you have any questions at all, please email me and I'll help you with that. So for that, we are signing off for today, and I'll catch you on the next lesson. Take care. So long.